of the Gabriel synthesis with a malonic acid synthesis. That is, you use the diethyl propane dioate molecule, remember, with the acidic carbon, hydrogens on this carbon, from which you can make a stable, not so basic enolate, which you can alkylate. So in order to just show you how this works to make the simplest amino acid without substituents, namely glycine, you just take this and you alkylate the nitrogen using this bromide derived from malonic ester. This bromide, by the way, you make from the malonic ester by the classical radical halogenation. So you use light and bromine, ONBS, and that puts the bromine in here. So you can do an SN2 reaction that gives you this dicarboxylate, and then you just hit on it with under hydrolysis conditions, which in one step, in one pot, will hydrolyze the two ester functions to the carboxylic acids. And of course, remember in the malonic acid, one of the carboxys falls apart to carbon dioxide, so this guy blows off. And under the same conditions, all in one pot, you also hydrolyze the imide here, the bis-amide function, to liberate phthalic acid, which you can recycle if you want. And there you have your amino acid. So what we have here, this nitrogen is derived from the phthalimide anion, and this piece is derived from malonic ester. It's a substituted acetic acid. Remember, we said that malonic esters, by alkylation, you can view them as synthetic building blocks for substituted acetic acids, where this is the piece that derives from the malonic ester, and then we had an R group. But here, because of this variant, we can introduce also the nitrogen. So that's the only difference. Of course, this would be useless for glycine. The beauty of that, and this is why we use malonic ester, is that this guy, reproduced again here, of course, has an acidic proton. And that's the one you want to alkylate at this stage. Okay? And so we make the anion under the usual conditions, some hydroxide or alkoxide. Then you alkylate. And remember, you can do branched, you can alkyl groups, because the anion is not very basic. And that introduces R. And then you go through the unraveling of the whole spinach that's sitting around. And that gives you a wide range of amino acids, essentially anything that is tolerable to, or that can be introduced through haloalkane. So this is by far more general type of methodology that also works in much better yield overall, although, in a synthesis in the exam, we can use both methods. And the third one is a variant of a couple of reactions, or a concept that we use in a couple of reactions. That's called the Strecker synthesis. And it is based on carbonyl chemistry. And it takes its origin from the addition of HCN to aldehydes and ketones. Remember, that gave alpha-hydroxy cyanides, also called cyanohydrins, common name. But the key point was that we have an alpha-hydroxy function and a nitrile function. Of course, a nitrile function on hydrolysis gives you carboxylic acids. So this was a way to make alpha-hydroxy carboxylic acids. And Strecker realized that if instead of HCN, he used ammonia together with HCN, which, when you mix ammonia, a base, and HCN, an acid, is actually ammonium cyanide, a salt. So you can use just ammonium cyanide, or you use ammonium as a different salt, like ammonium chloride, and the cyanide from another salt. But possibly the easiest way to do this is to just remember ammonium cyanide, or just use NH3 plus HCN. If you do that, remember that aldehydes and ketones react with amines to make imines in an equilibrium situation. And since this is under acidic conditions, ammonium, remember pK of ammonium is about 10, so this is reasonably acidic, just acidic enough to generate protonated imine. We have iminiumine in equilibrium with carbonyl. The nucleophile that's also floating around, namely cyanide, will attack the imine selectively over the carbonyl. Okay? And so instead of getting the alpha-hydroxycyanide, you get an alpha-amino cyanide. In this case, 2-amino-propane nitrile. These are isolated, and then in a separate step, you hydrolyze the nitrile function using typically acidic conditions, H plus H2O, and that gives you the corresponding amino acids. So here we can start with an aldehyde, and these two carbons eventually wind up as the or this carbon winds up as the stereocenter of the amino acid, and this methyl, in this case, or R group, if it's a generic aldehyde, winds up as the R group of the corresponding amino acid. So one can look at the, at a movie of that. Which goes through the whole mechanistic detail, imine formation, HCN addition, and hydrolysis. So here we form an imine. We've seen that before. Amine adds, protons shuttle around. This is the hemiaminal. Then you dehydrate by protonation. This becomes a leaving group. Water leaves. There's the iminiumine. And the iminiumine is then attacked by nitrile, as shown here. And then you hydrolyze the nitrile. This should be protonated. In the movie, they do it later. So this gives you another resonance form. Water adds to the nitrile carbon. You get this protonated species, proton folds off. This is a valence, it's a tautomer of an amide. So you tautomerize by protonating here and deprotonating here. That gives you the amide. And then the amide is hydrolyzed by the classic addition elimination. So now, belatedly, they're protonated. They should have been protonated earlier. But the action part is here. So you protonate here, right? That turns this into a good nucleophile, a hydroxycarbocation. Water comes in here. Proton falls off, tetrahedral intermediate. And then amine blows off by protonation and leaving group. And that is the hydroxycarbocation again. That's really a protonated carbonyl. And there is your amino acid. So this trick of using amines in conjunction with other reagents in reactions of aldehydes and ketones is one that nature uses frequently. I mentioned this before. And we've seen it at least twice before. One was reductive amination. Remember, we could take a carbonyl compound in the presence of an amine. Let's take methylamine. And that's set up in equilibrium under acidic conditions, at pH around 2, with the iminiumine. And if, at the same time, in this mixture, you have sodium cyanoborohydride, a hydride-reducing agent, the hydride attacks here and gives you the reductive amination product. The same principle is up there. You use the equilibrium, you trap the more reactive iminium. Second case was the Mannich reaction. In the Mannich reaction, we have an imine version of an aldol. Under acidic conditions means that we're not using an enolate, we're using an enol. The enol is the reactive form that reacts with a mixture of, let's say, formaldehyde, and let's use methylamine again. which is in equilibrium with its corresponding iminium ion under acidic conditions, such that the enol adds to make the corresponding amino metal cyclohexanol, in this case ketone. Okay? So again, we're trapping the more reactive species in equilibrium. Okay, so I'll lean back and enjoy the rest of this. The amide function is rather rigid because of the contribution of this resonance form. We know that already, so I'm just repeating this. And that actually makes polypeptides, essentially you could call it sticky. You can see this rigidity in the NMR. The barrier to rotation around this bond, typically in, say, butane, as we did in chapter 3A, in butane it would be 3 kcals or a little more, 4 kcals. And the barrier here is about 20. Okay? So by NMR, actually at room temperature, you can see the two cis and trans isomers, essentially, around this bond. If you warm the NMR tube in your NMR spectrometer a little bit, then it rotates fast enough that the signals coalesce. But otherwise, you can often see two different isomers when you have amides. Okay? So that is also very much useful in natural molecules when you have these large polypeptide structures that curve around and make globular-type structures. Everything is actually rather sticky and therefore slow. And this is an X-ray picture of a typical amide linkage. Notice that because of the overlap of this nitrogen with the carbonyl, that's an sp2 hybridized nitrogen. It's typical of amides. So the way we draw a tripeptide, again, I won't test for this, your amino end is to the left, the carboxy end is to the right, and then you do a zigzag notation of the so-called main chain from which the R group emanates. If the zigzag goes up, let's call it zig, then the R group is wedge. If it goes down, let's call it zac. It goes to the back, there's zig again, and so on. Okay? And that way you can line up one amino acid after the other with various R groups, and all these stereocenters are S. So the linear sequence of amino acids in up to several thousand units is depicted by abbreviations of the names alanine, glycine, and so forth. There are 3-letter codes that are part of that table that if you go into biochemistry you have to remember. That's called the primary structure. So that just tells you the sequence of amino acids that make up the polypeptides. But these guys, of course, can form some much more complicated arrangements. And so there's secondary, tertiary, and quaternary structure. Well, secondary structure is basically a hydrogen bonding further 3-dimensional arrangements. And there are two extremes. One is 2 polypeptide chains line up next to each other. Okay? And carbonyl of one amide function finds a proton of a second amide function in the other chain and makes a hydrogen bond. Hydrogen bond, remember, between oxygen and hydrogen of a nitrogen molecule on the order of 3-4 kilocalories per mole. Okay? Weak bond. But if you have 8,000 of these guys lining up, you multiply 3 to 4 kcals with 8,000, you get extremely rigid frameworks that make up your fingernails and hair and other very rigid structures. So that's called a pleated sheet structure because the stereocenters induce, so there the two arms line up again, these kinks as you go down the line, this kind of dipolymer type arrangement. Okay? So it looks like this. The alternative is a helix, as shown here. Where every third or so amino acid, let me see a better one, let's see this one. This amide here, this carbonyl finds this proton here, and this is 1, 2, 3, 4th amino acid down the chain, finds a hydrogen that's perfectly arranged to make a hydrogen bond, and in this way it has to coil, and that coiling is rhythmical, if you wish, because all the stereocenters are S, they have the same handedness, so they coil by necessity as a helix. Okay? It's preordained, or pre-set up. Okay? There are about 3.6 amino acids per turn. So that forms this type of secondary structure. Then there's tertiary structure, where there's further folding and aggregation. One very famous one is the so-called superhelix. If you take 2 helices, secondary structure of a helix, as a helix, and take the 2 of them together and start coiling them, winding them up, that's called the tertiary structure. That's called the superhelix. And these kinds of arrangements are typical of the so-called fibrous proteins, muscle, blood clots, keratin. Keratin is in wool, nails, and hair. And the breakdown of this type of tertiary structure is actually part of denaturing. Okay? So if you take milk and you have tea with lemon and you want to add some milk under the acidic environment, it'll curdle. Okay? That's denaturing. Or you fry an egg and it'll turn white. That's not a chemical reaction. The same polypeptide, but you're destroying the tertiary structure of that particular peptide. Okay? So a very minor, really, change. And tertiary structures also, by all this coiling and arrangement, give rise to these pockets that are typical of enzymes. So here's a digestive enzyme called chymotrypsin. It's made of 3 polypeptide strands, 245 amino acids, and they coil up to make this what looks like completely, indecipherable array. One can blow this up, and you can see the individual amino acids coiling up, making hydrogen bonds, and all that kinds of stuff. Here's another rendition of it. And it's in these holes that certain molecules fit perfectly. In this case, it's a digestive enzyme, so you can imagine a hamburger fitting in here perfectly, and it starts chewing away. Well, not quite the hamburger, but the fats and the protein in your hamburger. These structures fit in and get hydrolyzed. Okay? Remember, amides are very stable to hydrolysis, so you need some help, and the enzyme provides that help. And then there is quaternary structure. That is, you now can, unfortunately it ends there, but you can have several of these larger coiled aggregates getting together and assembling to something even bigger. And a very famous one, of course, is hemoglobin. Okay? It's got 4 of these arms called the 2 alpha arms, 2 beta arms, whatever that means. They coil up and they attach to each other by hydrogen bonding, hydrophobic interactions, and the like. And it's a huge transportation system for a tiny little molecule, namely this heme, so-called heme piece, which is shown here again. It's this polypyrrole, cyclic polypyrrole. The red shows that this is actually aromatic if you count the electrons. And it functions as a ligand to hold iron in its middle. So this huge thing is basically a vehicle to get the iron that's held by this ligand transported in your blood. And it's the iron in this so-called heme that binds oxygen. Okay? And it's the oxygen that is transported by your blood. And the color of this complex is red, and this is why your blood is red. Okay? Purely an organometallic compound that gives you the red color. And Angelina Jolie knows this very well. And so all vertebrates that have red blood cells are based on this principle. So oxygen binds to here, and it's a very weak complexation. It gets transported wherever oxygenation is needed, and then the oxygen comes off. Okay? And one of the reasons cyanides is so toxic in other CO, carbon monoxide, is because they bind to iron much more strongly than oxygen does. Iron carbonyl complexes are well known, very strong bond. So basically, you shut down the oxygen transport through your blood, meaning that you essentially internally suffocate because you can't get oxygen anywhere. Although other things happen also. There's some catalytic one-electron transfer compounds that are also based on iron. Everything is shut down that contains iron, and so your body just shuts down. So in the sequence, here are the amino acids. That's the primary sequence. Amino acid 1, 2, 3, 4, 5. They start aggregating either pleated shields or alpha helix. These guys start aggregating to larger pieces, in which, or into larger aggregates, in which you notice the pleated sheet or helix structure can alternate. Okay? It depends on the particulars of the protein. So this is tertiary structure, and then you can aggregate even further to get quaternary structures. And we'll learn how to make dipeptides and tripeptides next Thursday. Thank you.